All right, so at the point of this video, we have talked a lot about concavity. We have talked about first and second derivatives and how they're related to critical numbers and inflection points and the first derivative test. And so what we're going to try to do now is look at this thing called the second derivative test. And the second derivative test is a sometimes easier way to determine if a function has a local max or min, just using, as the derivative test says, the second derivative. And an important idea that helps us understand the second derivative is this thing called the quadratic approximation. So that's what we're going to do in this video. We're going to focus on just, a quick just observation that the first derivative of the function f of x. There's something important about that quantity called f prime of x. We use the first derivative to find what we call the tangent line. And the tangent line can be found by using the function value at a specific value of x. And then we get to use the first derivative at that value and then multiply by x minus a. And this is an important formula that we're very familiar with called the tangent line approximation of the function f of x at x is equal to a. And sometimes we just call that L for linearization. Okay. Now, that's the first derivative. And we're familiar with what we can do with the first derivative. We can figure out if the function, we can look at a sign line for f prime, and we can figure out critical numbers of the function f when the derivative of that function is equal to 0. That's a critical number of f. Figure out if it's positive or negative. That will tell us that the function is increasing and then decreasing. And then we could say that we had a local maximum at this point. That would be the first derivative test. But one thing that's going to be interesting for us to notice is that there is also a second derivative of the function f of x. Okay, and we're familiar with it, and we know we can do sign lines also with the second derivative. But one thing that we're going to find important is that there is a formula that is the natural equivalent of the linear approximation, and it's called the quadratic approximation. The quadratic approximation of the function f of x at a point x is equal to a. And the quadratic approximation, its formula is the formula you got from the linear approximation, and then you just need to add on an extra term, which is 1/2 the second derivative at a multiplied by x minus a squared. So this formula right here, this is a formula for the quadratic approximation, and you should be able to just plug in everything you need to figure out the formula for that. So I wanted to show some pictures of what the quadratic approximation looks like, and then we will try to do an example computing its formula. So here what you're seeing is in black here, the black dotted line. You're seeing one of the most important, probably one of the most important functions in statistics for sure. That black dotted line, this is called the bell curve, okay, or called the Gaussian or normal distribution. It looks like a little bell-shaped curve. And we're seeing two different other functions on top of this. We're seeing a red line called the tangent line, and that's called L of x, and you can see the formula here. There's also a formula Q of x called the quadratic approximation, and you can see that it is a squared function, and that is the function shown in blue. And you can see that that blue function is a quadratic. It looks like a parabola. And the most important thing is that the number in front of the x squared is a negative number, which means that that parabola is going to open downward. Okay? So if you pick different values, pick different points A, pick different values A to compute this quadratic approximation at, your graph are going to change. You can see that there's a tangent line to the black dotted line, and then you can also see that there is the quadratic approximation. It's not a straight line, it has a little bit of bend to it. And if you were to zoom in, we would see that that tangent line is a tangent line. It's approximating the function at this point. But the blue curve bends and conforms to that function just a little bit better. And again, here is the formula for it. It's a quadratic because there's a squared here. But the minus sign in front of that x squared term means that that quadratic is bending downward. Okay, this function is concave down at that point. Okay, so what we're going to see is if you move to different points, you'll see the linear and the quadratic approximation change. And something very interesting happens when you put in 0. 0 is a critical point, right, of the function. You can see that the derivative is equal to 0 at this point. So that's why the tangent line has 0 slope. And the quadratic approximation is simply negative x squared plus 1. So the plus 1 shifts it up by 1, and the negative x squared means that it's a parabola opening downward. So the e to the negative x squared function is the bell curve, and sometimes it's a hard function to work with, as we'll see later on in this course, but it can be approximated using a very nice, easy function called a parabola, or the quadratic approximation. So I think it would be good that you get a little practice with this quadratic approximation, because it's going to be the key to the second derivative test that we'll do in the next video. So here are some functions, and I would want to be able to take any of these functions and find the quadratic approximation to any of these functions at any value x is equal to a of your choice. Okay, so we'll just pick one of these functions at random, 31 through 36. I don't know, I'll pick 34. Okay, so there's a function in number 34. Okay, it's x cubed minus 6x squared minus 3. Okay, now you should be able to pick any value of x is equal to a. Why don't we say 2 in this case? I have no idea. Just pick 2. And now let's find the quadratic approximation by finding the linear approximation, and then you're going to add on 1/2 the second derivative at 2 multiplied by x minus 2 squared. So the first thing you need to find, there's a step 1, the linear approximation, and then you're going to add on the extra piece. So the linear approximation is the function evaluated at 2 plus the derivative evaluated at 2 multiplied by x minus 2. Okay, this function evaluated at 2 is equal to 8 minus 24 minus 3, which is negative 19. If I'm understanding that correctly, let's put a 2 in, you get 8. 2 squared is 4, minus 24 minus 3, minus 27. I agree with the minus 19. So the derivative function, f prime of x, is 3x squared minus 12x. So f prime at 2 is equal to 3 times 4 minus 24. 12 minus 24 is negative 12. So we know that the linear approximation at the point, let's see, 1, 2, right, should have a negative slope, which it does, and looks like it has a y-intercept of a positive number, or maybe a negative number. It's kind of hard to tell, but we can see that the function evaluated at 2 is minus 19. It is below the axis. So we'll see what happens when we find the linear approximation. It is negative 19 plus negative 12, so minus 12 times x minus 2. There is the linear approximation. Okay. So let's go ahead and find the quadratic approximation now. It would be negative 19 minus 12 times x minus 2 plus 1/2 the second derivative, and the second derivative is equal to 6x minus 12. So the second derivative at 2, oh, that's convenient. Second derivative at 2 is equal to 0. So then you get x minus 2 squared. Okay, so yeah, we must see that our quadratic approximation, it doesn't actually have any linear quadratic pieces. Okay. So that would be that formula in use. If there was a number here, I would have divided by 2, and then I would have just written that multiplied by x minus 2 squared. And you could have left your answer like that. So if you wish, I could put plus 0 times x minus 2 squared. Okay, let's check our answer and see how we did. The function is, let's see, x cubed minus 6x squared. X cubed minus 6 times x squared minus 3. Okay, and we can put in the specific value of 2 that we wanted. And as promised, there is the linear approximation. We can see it has a negative slope. And if you expanded this out and put it in y equal mx plus b form, you would find that it has a y-intercept of positive 5. And we can see that the linear and the quadratic approximation are the same here. At that point, it looks like we had a place where the second derivative was 0. And what's really interesting here is that the function goes from being concave down at that point to concave up. So at 2, the reason we didn't have a quadratic piece is because at 2, our function had an inflection point. Okay. So there's an example, another example of the quadratic function, and you should be a quadratic approximation. And you should be able to do any of these functions here at any value that you find. You could create a graph of it in Desmos and see how your linear and quadratic approximation pieces looked.